Welcome back. So I'm going to implement the iterative solution now. And the first thing I need to do, of course, is define the function itself. So what do I call this one? Depth first recursive, depth first iterative. You could definitely do something simpler. Okay, so it accepts a starting node. And there's a couple of things we have to get out of the way. We have to make our stack, we have to make our result array, and our visited list, or not a list, object. So visited, we could actually just copy this from up here. Results and visited. But I also need to make my stack, and I said the stack is going to be, I'll just call it stack, an array as well. But we need to put the start in there. Remember this line here, add the starting vertex to the stack and mark it visited. Well, I'm just going to do this rather than pushing it, just have it initialized there. Then after that, we need to mark it as visited. Let's just make sure we did everything else. Made the function, made the stack, created a list, add the, okay, this is all good. We need to add the starting vertex, we did that, mark it as visited, and then we'll add our loop. So I'm going to set visited. I'll make this just a separate line just so we can see these are our variables, our declarations. Visited of start equals true. Again, you could just use an array to manage what's been visited. Let me close this, by the way. But I like doing it this way with an object. It's just more explicit. Okay, now we need to do our while loop. So while there's something in our stack. So I'm just going to do while stack.length. You could do greater than 0, but stack.length is easy because as soon as we hit 0, we're done. It will be falsy. While the stack has something in it, pop the next vertex from the stack. If that vertex hasn't been visited yet, mark it as visited. So let's start with that. I'm going to make a variable first to store what we're popping off. So I'm just going to call it, I don't know, current vertex equals stack.pop, just like that. Then we need to actually add current vertex to our result array. So result.push current vertex. So that's what we'll return at the very end. And then we're going to go to each of its neighbors. And before I do that, rather than redefining current vertex each time through in this loop, I'm going to come up here and just do let current vertex, and then down here, give it a value. Minor thing, but I just don't like, constantly reinitializing current vertex inside a loop. Now we need to add each of its neighbors to the stack. Well, if they haven't been visited yet. And let's just start by accessing the neighbor. So this dot adjacency list of current vertex. So that's going to give us, if we're talking about A, it will give us an array that contains B and C. Okay, so this dot adjacency list current vertex dot for each, kind of a long line. I'm going to call it neighbor. You could call it, I don't know, connection, pal. I wouldn't call it pal, probably not. So what do we do? Well, if it has not been visited, so if inside of visited there is nothing for neighbor, if that's the case, we need to make sure that it has been visited. Okay, so we're going to visit the neighbor, and then, well, we'll set it to be visited, then stack.push neighbor, just like that. Okay, and we're basically done. We just have to, at the very end, return our correct result. And as we're going through this, how about right here, we do a console.log of the stack so we can see what we're working with. Okay, so I'm going to execute our code, and I'll call g.depthFirst iterative with A. And what do we get? If I can make this larger. Okay, so first of all, the order we get is different. And we can talk about why in just a bit, but it still is depth first. If you don't remember, let me do the same thing for recursive. We got A, B, D, E, C, F. So the recursive version was A, B, D, E, C, F, which is still depth first. The iterative version, instead of going A and then B, we actually end up going A and then C. But as long as we're following this path down and following one of C's neighbors and its neighbors and its neighbors, it's still depth first. It's just we started with C rather than B because of the way that our code works, and you'll see why. So A, C, well, we go to C's neighbors. We've already been to A, so we go to E. Then from E, we have three choices. We've already been to C, so we have D or we have F. And our code goes to F next. And then from F, we could go to E. We've already been there. So we go to D. And then from D, we could go E, F, or B. Well, we've already done this. We've done this. So we go to B. But it still is depth first. We go here, 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 here. So think of it this way. If this is our adjacency list, it's the same for both versions. What we are doing in the recursive version, we started at A. We go to B. Alphabetically first, or whatever's first in this adjacency list is visited first. So A to B. Versus in the iterative version, we went to A to C. And then from C, if we look at C, we go to E. And from E, we've already been to C, and we go to F. We're taking whatever is at the end, or we're working from this direction, if that makes sense, from the end of the adjacency list rather than from the beginning. So now let's walk through why this works. Let me clear this. And let's do iterative of A. This is what our stack looks like the very first time through. We have A. Okay, so we visit A. We go up through our code a bit more. We're going to visit it, add it to the result. So our result now contains A. Then for each neighbor, well, we have two, B and C. We add them both in. So we popped A off, it became empty. Then we add B and C. Cool. So then what we're going to do is visit C because we are popping off the end. So we're going to C next. And then we're going to add it to the result. So our result looks like A, C. And then we go to C's neighbors and we push those in. So we end up with B and E because we've already visited A, we don't add it in. So then next we pop off the stack, we go to E. So we visit E, A, C, E. Okay, so you can see that B is just patiently waiting here. This, if we were doing breadth first, we would go immediately A to C and then back to B. But it's depth first, so poor B is waiting. Or in the recursive version, we go A to B and then C is waiting. Anyway, so we keep going and you can see that we end up with E's children or E's neighbors, F and D are both added in. And D is first and then F, but we pop off the end, so then we visit F next. And then from F, we don't have anything to add because we've already been to E and to D. Well, we haven't been to D, but we've already added it into our stack and we've already visited it, meaning we've set it to be visited true. Otherwise, D would get pushed in there again. Okay, so then we pop F off. Now we have B and D. We start with D. We pop off the end. And then finally we get to B. It's the last thing added. So we're using a stack, an array, to keep track of sort of where we need to go back to, right? We're going here. We know we need to visit B at some point, but we start with C. And then from C, we go to E. And at E, we're going to go to F, but we also need to remember to go to D. So we add D in as well. But poor B has been waiting this whole time. It's depth first. So I do think for some people, I think the iterative version is easier to understand. But I think that the recursive version is important to understand why it works. It's a classic use case for recursion, graph traversal, that is. And I think, if you can get one of these, if you can understand, you can walk through it, you're good. So this is the iterative version. We saw the recursive version. They both are depth first. We do get a slightly different order. There's not one exact precise depth first order for any given graph. So there are different orders, but they are depth first. Okay, next up, breadth first. We're only seeing one solution.